So if we store the output of the summation into a variable called x, the next step in the architecture is to create this segment, which takes x as input, and it will output the scale.product attention. So let's go through each one of these operations one by one and see how to construct these three vectors called q, k, and v. Q is short for query, k for key, and v for value. Although the concepts in computer science are a bit convoluted, we can basically think of these three matrices as projections of the input, which is x. So basically take x, multiply it by a matrix, and create these three matrices. The way it's done numerically is first to take the x, which is the summation of the position and token embeddings. In our case, it is a matrix of size 3 by 10, T by D model, and then pass them to a fully connected layer. The shape of this layer would output a T by D model times 3. So the idea is pretty straightforward. Create three projections for x and deconstruct them into three matrices of size 3 by 10 and call them query, key, and value. So numerically, this is what we did here. Each one is a 3 by 10 or D model matrices. Next, we'll use the idea from self-attention, which is basically to take different projections of the input and eventually pass them through a softmax to create probabilities or the amount of attention that should be paid to the inputs. So the idea is similar to the original self-attention architecture. To do that, we get the two projections, Q and K. We do a matrix multiplication, so Q, K transposed. That's basically this part of the architecture, the math mul of Q and K. And then the next step is scaling. It's some sort of a normalization, so square root of D model. So square root of 10 in this case. And since Q and K have the shape 3 by 10, and therefore K transposed has a shape 10 by 3, the output would be a matrix of 3 by 3, which is basically T by T. Hopefully at the end we'll have the amount of attention that we would pay to the word T when we want to predict the word T in the output. So for the first word, this is the amount of attention. For the second word, this is the amount of attention that we should pay to each word in the input. The first word, the second word, and the third word. So how do we get from step 1 to step 3? One consideration that's optional in the transformers architecture is masking subsequent words. So the idea is, if I want to predict the first word in the output, I should only see the first word in the input. It would be kind of cheating to look at the subsequent words because the information, the word that I'm trying to predict, would be in the subsequent words. So for masking, we replace the upper triangle with minus infinity so that the model will not see the information from subsequent words. And after the masking, if we use softmax, the minus infinities will turn into zeros. And when I want to predict the first word in the output, the value of my attention here now would be 1 for the first input word, 0 for subsequent words. So to predict the first word, I can only look at the first word in the input. To predict the second word in the output, I can now look at the first word and the second word in the input. And for the third word, we can look at all the 3 words in the input. So these are the amounts of attention. The softmax is calculated at the final dimension or the column. And that's how we get the results up to this point. Then the model architecture suggests we take the output of the softmax and do a matrix multiplication with the value matrix that we set aside. So the value matrix contains information about the input, and if we multiply that by the output of the softmax, which shows our attention to each word, we'll get the attention adjusted inputs. So that's what we will do here. To get the attention, which is a function of Q, K, and V, first we calculate the softmax, or the amount of attention, and then do a matrix multiplication with V. If we remember, the output of the softmax was a 3 by 3, and if we multiply that by V, which is a matrix of size 3 by 10, these are T's, and 10 is D model, we'll end up with a matrix of size 3 by 10. 3, the number of rows, 10, the number of columns. Then the next step, to predict the probability for each word in the output, word 1, 2, 3 in the output, over the distribution of every word in the vocabulary, we'll use a simple fully connected layer. So we input our attention to this fully connected layer and create 3 by the vocab size, in this case 6. So the number of columns would be now 6. So these are logits, so they can be unbounded, negative, positive. To turn them into probabilities, we'll pass the logits to a softmax, and these are the probabilities. So this is the probability that the first output is the first word in the vocabulary, second word, third word, all the way to sixth word. So now we can actually see what the predictions are. If our input is answered the following, and this is the result of the softmax, for the first prediction, here, the first row, these are the probabilities for different words in our vocabulary. So the first word, 0.22, is the probability of the answer. If you look at the maximum, 0.24, it's the fourth word, so it's please. So our output prediction would be please. This is the first word. The second word would be the maximum of this vector, which is the first index, which is answer. Please answer. And for the third word in the output, it would be the maximum of this row, the third word, which is also the first index, answer. Of course, we have not trained this model, so please answer doesn't make sense. We have to use cross entropy loss to update the weights in our model and make the prediction closer to the following question.